morning, everyone. This is Anika Rahman, and I want to thank you all for giving me the opportunity to present our research titled Assessing and Predicting Air Pollution in Asia, a regional and temporal study from 2018 to 2023 at the 4th International Conference on Computing and Information Technology Trends, CCITT 2025. This study explored the patterns, impacts, and predictions of PM 2.5 levels across Asia, emphasizing regional disparities and health implications. Air pollution, particularly PM 2.5, remains a critical issue in Asia. Our research spans 5 years from 2018 to 2023, focusing on trends across five distinct regions: Central, East, South, Southeast, and West Asia. South Asia emerged as the most polluted, with countries like Bangladesh, India, and Pakistan showing consistently high pollution and death rates. In contrast, East Asia had the lowest pollution levels. Employing K-means clustering, we categorized countries into low, moderate, and high pollution groups, while the ARIMA model provided accurate predictions of 2023 pollution levels with robust metrics such as R square at 0.86. These findings underscore the urgent need for targeted interventions to mitigate pollution and its associated health risk. So, we know air pollution is one of the most significant public health and environmental challenges worldwide. PM 2.5, due to its microscopic size, poses severe health risk, including respiratory and cardiovascular diseases. Asia, housing over 60% of the global population, faces some of the highest pollution levels globally, driven by rapid urbanization, industrialization, and population growth. Our study aims to analyze trends in PM 2.5 levels across Asia, understand regional disparities, and forecast future pollution levels using machine learning techniques like K-means clustering and ARIMA modeling. Now, we are focusing on literature review. In recent decades, air pollution in Asia has become a critical concern, severely affecting both food security and public health. South Asia accounts for 37 of the world's 40 most polluted cities, with millions of preventable deaths and crop damage that impacts food for 94 million people annually. Biomass burning contributes up to 60% of haze events in Southeast Asia, exacerbating health and sustainability challenges in regions like India, Nepal, Bangladesh, and Pakistan. Few studies show that air pollution reduces life expectancy by about 3 years for 660 million people and is linked to nearly 350,000 pregnancy losses annually. Various models have been developed to predict air quality. A hybrid model combining LSTM and MVO forecast pollution from power plants, while a temporal sliding LSTM framework also shows promise. Recent advancements integrate machine learning techniques like the VMD, CSA, CNN, LSTM model, which achieved high prediction accuracy for AQI in Chinese cities. Similarly, studies in Varanasi found random forest and decision tree models highly effective for real-time air quality predictions. These innovative approaches highlight the role of predictive models in urban planning and pollution management. Now, we are focusing on our methodology section. At first, we utilized air quality data from IQ Air, covering PM 2.5 levels in Asia from 2018 to 2023. This dataset includes information on regions, countries, PM 2.5 values, population, area, and air pollution related death rates. While it originally covered 38 countries, it was refined to 36 for ARIMA model predictions due to data limitations. Then we performed few data pre-processing to ensure the data's usability. At first, PM 2.5 values were converted to numeric with invalid entries replaced by zeros. Population and area columns were cleaned by removing commas and converting to numeric format. A new feature, population density, was calculated for each country. Then data was filtered to include only Asian countries with missing PM 2.5 values filled with zeros. And finally, countries were classified into 5 categories: Central, East, South, Southeast, and West Asia. Then we examined PM 2.5 trends over time. That means temporal analysis into 2 categories. The first one is regional analysis. It involved time series plots for PM 2.5 levels in 5 Asian regions revealing regional patterns and changes. And the second one is overall Asia analysis, which aggregated PM 2.5 levels across regions, offering a comprehensive view of air pollution trends from 2018 to 2023. And then we performed death rate analysis. The impact of air pollution on mortality was analyzed for 2018 to 2021. Regional death rate analysis was used bar plots to visualize average death rates per region, highlighting disparities. And secondly, a focused analysis on South Asia examined country specific trends, identifying nations most affected by air pollution. And then we performed correlation analysis. We conducted three key analyses to uncover relationships: PM 2.5 and population density, PM 2.5 and death rates, and finally PM 2.5 and mortality trends. So, the first one, a correlation was calculated for 2023 to determine if densely populated area experience higher pollution or not. Number two, average PM 2.5 levels and death rate from 2018 to 2023 were compared, uncovering the health impacts of air pollution. And finally, relationships between PM 2.5 data from 2018 to 2021 and death rates were explored to assess longer term effects. Then we perform clustering. To categorize countries based on their air quality in 2023, we applied KMS clustering. PM 2.5 data was standardized and the optimal number of clusters was determined using the ELBO method. This analysis highlighted distinct regional pollution patterns, offering insights into air quality profiles. And finally, the ARIMA model forecasted PM 2.5 levels using data from 2018 to 2022. Predictions for 2023 were evaluated using metrics like MAE, MSE, RMSE, and R square. For 2024, forecasts were made, but evaluation metrics are pending because of actual data. The model's performance was used using four evaluation metrics: mean absolute error or MAE for the average prediction error, mean squared error or MSE for the average squared prediction error, root mean squared error or RMSE to measure error size, R square to quantify how well the model explains variance in the data. This comprehensive methodology enabled us to analyze and predict air quality trends and their impacts effectively. Now we are moving on result analysis section. At first, I will present the temporal analysis of PM 2.5 levels across various regions in Asia, spanning from 2018 to 2023. This section provides a detailed examination of air quality trends, offering insights into the environmental challenges faced by different regions and countries. Let us begin with South Asia. As depicted in Figure 1, the region showcases significant variability in PM 2.5 levels. Bangladesh records the highest level, rising from 97.1 to 79.9, indicating a traveling increase in pollution. Similarly, India shows an upward trend, reflecting deteriorating air quality. On the other hand, Pakistan exhibits a slight overall decrease with notable improvement between 2020 to 2021. Nepal experiences a steady increase, while Sri Lanka, though maintaining a relatively lower levels, shows a moderate upward trend. And for the Maldives, data availability is limited, emphasizing the need for improved monitoring. These trends underline the urgent need for comprehensive and targeted interventions to tackle pollution in South Asia. Now, moving on to Central Asia, illustrated in Figure 2, we observe diverse air quality patterns. Kazakhstan shows a slight increase in PM 2.5 levels in recent years, while Uzbekistan experiences fluctuations peaking in 2020. Kyrgyzstan and Tajikistan face data gaps after 2020, which hinder a full understanding of recent trends. These gaps highlight the critical importance of enhancing monitoring infrastructure in the region. Addressing this limitation through techniques like imputation may help, but could also introduce inaccuracies. In Southeast Asia, as shown in Figure 3, trends reflect significant variability. Indonesia experienced a peak in 2021, followed by a decline, while Thailand shows a slow but steady rise. Vietnam also exhibits fluctuations, whereas countries like the Philippines and Singapore maintain consistently lower levels. Cambodia, in particular, demonstrates high variability in air quality, highlighting the region's diverse pollution patterns and the need for tailored policies. Next, let us discuss East Asia, visualized in Figure 4. China shows a consistent upward trend, underscoring persistent pollution challenges. Conversely, Japan maintains the lowest PM 2.5 levels in the region, reflecting stable air quality. South Korea and Taiwan exhibit gradual increases and fluctuations, respectively. Mongolia reports alarmingly high levels, peaking in 2021, which underscores severe air quality concerns. This region illustrates varying degrees of progress and challenges necessitating region specific interventions. Turning to West Asia, as depicted in Figure 5, we observe a wide range of trends. Turkey shows relatively stable levels, while countries like Saudi Arabia, Iraq, and Kuwait exhibit significant fluctuations. Bahrain and the UAE face worsening pollutions, whereas Israel and other countries show moderate stability. Incomplete data for countries like Armenia and Azerbaijan limits comprehensive assessment, again emphasizing the need for better monitoring system. Finally, Figure 6 provides an overview of Asia, showing the average PM 2.5 trends across all regions. As you see, South Asia reports the highest levels in pollution after a slight decline during 2018 to 2020. Central Asia and Southeast Asia display notable fluctuations, while East and West Asia maintain relatively lower levels. However, these overall trends are limited by data gaps, particularly for countries like the Maldives and Kyrgyzstan. In summary, the diverse patterns observed across Asia highlight the varying impacts of air pollution and the effectiveness of regional policies. While some areas have achieved significant progress, others continue to grapple with severe challenges. Addressing data gaps either through enhanced monitoring or advanced statistical methods is essential for informed policy making and the development of effective air quality management strategies. Now we are focusing on death rate analysis. At first, regional death rate trends. Figure 7 highlights the variations in death rates due to air pollution across Asia from 2018 to 2021. Unsurprisingly, South Asia, as you see, South Asia consistently recorded the highest death rates, driven by severe pollution levels in the region. Central Asia followed with high rates, while Southeast and West Asia showed moderate levels with some fluctuations. Notably, East Asia had the lowest death rates, likely due to effective pollution control measures. Examining specific trends, 2019 showed South Asia maintaining the highest rates, while Central Asia saw a slight reduction. In 2020, most regions observed a decline in death rates, likely linked to the global pandemic in, induced slowdown in activities. However, rates rose again in 2021, especially in Southeast and Central Asia, underscoring the persistent challenges of managing air pollution and its health impacts. Secondly, turning our attention to South Asia, Figure 8 provides a closer look at death rates within the region. Nepal consistently experienced the highest death rates throughout this period. Pakistan followed, while India and Bangladesh showed slightly lower but still concerning trends. Sri Lanka exhibited moderate levels, and the Maldives consistently recorded the lowest death rates. Overall, these trends remained relatively stable over the years with only slight fluctuations, emphasizing the need for sustained intervention to reduce mortality caused by air pollution. Next, we explored the correlation analysis. At first, we explored the correlation relationship between PM 2.5 levels and population density in 2023. The correlation coefficient was approximately minus 0.20, indicating a weak negative relationship. This result visualized in figure 9 suggests that higher population density do not necessarily lead to higher PM2.5 levels. Factors such as geography, industrial activities, and environmental policies likely have a greater influence on air quality than population density alone. These findings stress the importance of adopting comprehensive policy measures that account for multiple factors beyond population density to address air population air pollution effectively. As you see, figure 2 reveals a moderate positive correlation of 0.63 between average PM2.5 levels 2018 to 2023 and death rate 2018 to 2021, suggesting that regions with higher pollution levels tend to have higher mortality rates. When analyzing data from 2018 to 2021 alone, the correlation coefficient was slightly lower at 0.57. This growing correlation with more recent data underscores the increasing impact of prolonged exposure to high pollution levels on health. It highlights the importance of incorporating the latest data for a more accurate assessment of pollution's health impacts. Well, now we employed the K-means algorithm to categorize Asian countries based on their PM 2.5 levels in 2023 using the ELBO method. Uh, as you see, here in figure 11, three clusters were identified representing low pollution, moderate pollution, and high pollution. These results show clear distinctions uh, among countries based on their pollution level, with each cluster color coded for clarity, as you see here. But uh, table 1 summarizes the PM 2.5 ranges corresponding to each cluster. So, for countries like the high pollution cluster, immediate actions such as stricter emission controls, investment in air purification are necessary. For the moderate pollution cluster, regulatory measures to curb pollution sources should be prioritized alongside countries' air quality monitoring. Countries in the low pollution cluster should focus on sustaining their current levels by reinforcing policy that promote clearer technologies and renewable energies. This clustering analysis offers valuable insights enabling policymakers to design and region specific strategies for improving air quality across Asia. Now we are focusing on our prediction model, that is ARIMA model, and its evaluation metrics. To forecast PM 2.5 levels, we employed the ARIMA model using data from 2018 to 2022 for training. The model's predictions for 2023 were compared with actual values to assess accuracy. The model was further trained on 2018 to 2023 data to predict PM 2.5 levels for 2024. However, this forecast awaited validation due to the unavailability of 2024 data. And now we're talking about evaluation metrics. The performance of the ARIMA model for 2023 was assessed using metrics like mean absolute error MAE was 3.99. The mean squared error or MSE was 33.80 and root mean square error RMSE was 5.81. These low values indicate that the model's predictions were generally accurate with minimal errors. Additionally, the R square values of 86% demonstrate the model's strong capability to explain the variance in PM 2.5 levels. These metrics validate the ARIMA's model's effectiveness, though further validation with 2024 data is essential for assessing its long-term reliability. So, as we conclude this presentation, let me summarize the key outcomes of our research on PM 2.5 pollution trends across Asia from 2019 to 18 to 2023. Our study used the ARIMA model to analyze and predict pollution levels, shedding light on notable regional disparities among 36 countries. We categorized these countries into three distinct pollution patterns: low, moderate, and high, based on their PM 2.5 levels in 2023 only. So, this classification provides critical insights that can guide targeted policy development, enabling countries to implement appropriate mitigation strategies. While This study focused on Asia only. It also sets the stage for future research. Our next step include extending the analysis globally, incorporating data from Europe, Africa, and other regions. Additionally, we plan to integrate alternative predictive algorithms to further enhance the robustness of our findings. This will allow us to provide a more comprehensive analysis and comparative insights. Our findings our findings emphasize the crucial role of continuous air quality monitoring and predictive modeling in understanding and addressing the health impacts of air pollution. As urbanization accelerates, it is essential for policymakers, environmental agencies, and researchers to collaborate and adopt a data driven approaches. By doing so, we can develop sustainable solutions to combat air pollution and safeguard public health across rapidly urbanizing regions. In conclusion, this study serves as a call to action for all stakeholders to prioritize air quality impacts. With that, I thank you all for your attention and interest in this topic. If you have any questions, then please feel free to share your thoughts or ask for further clarification. I would be happy to address them. And here are the references. Thank you.